This is Network Science, and today in this lecture we are going to cover the topic about percolation. Percolation in network science means that we are removing some nodes from the network, of course together with the edges, and we are interested to see and investigate the effect of this node removal. Now let's give two motivational examples which are kind of opposite of each other. One is about the routers on the internet, and there is a claim which says that about 3% of the routers are inactive at any point in time. And now the question is that how comes that the internet still works even with this inactive, with this although low percent but still inactivity. The other example is disease spreading, or if you want gossip spreading, or these kind of things, so information spreading on a network. And now if we think about vaccination, then from the disease point of view, we are with the vaccination we are taking out a person from a network, and in this case, I mean in this sense, we are basically deleting that node from the network, remove the node from the network. By the way, giving vaccination to one person has some secondary effect, namely that the vaccination not only cures a person, but also it prevents the spreading of disease. Well, as we know it these days, especially. Yeah, so the percolation, of course, by node removal we mean random removal, and this could be done in multiple ways, of course. For example, just uniformly at random, so each node should get the same equal probability to be removed, or there could be other methods as well, which are, for example, proportional to the degree. So we can say that starting from the largest degree, which could be useful, for example, for vaccinations, or we can also start with the largest betweenness centrality value and so on, or any other centrality values as well. And of course, this could be done also with randomness. So the higher the centrality of a node should get a larger probability to be selected for removal. Now let's discuss first the uniform random removal. So percolation with uniform random removal. Okay, now let's say that phi is the probability that a node is in the network is presented. So we can call this state as being occupied in this terminology. So if this parameter phi is equal to 1, then everybody is occupied in the network. So that means that every node is present. And the other extreme case, when phi is equal to 0, then all the nodes are removed. So nobody is occupied in that case. And in this fourth figure, what you can see is the two extreme cases, so phi equal to 1 and phi equal to 0, and some in-between values, namely 0.7 and 0.3. Hope you can see it. And you can also see that basically in the experiment which we are now drafting and discussing, what we are doing is that we basically never really delete a node from a network. We just make it inactive or unoccupied, basically, or inactive, let's say. And so those which are inactive nodes, or well, removed basically, they are kind of shown here with gray color, whereas the black nodes, the black color nodes together with their edges, if an edge has two nodes, two n nodes which are all inactive, so all actives, then the edge itself is also black colored. Then so these are the kind of notation, visual notation, which we are going to see. And soon you will also see that we are going to think in a backward manner. Okay, so we are interested in a cluster, the component which remains connected during the percolation. So so basically a connected component. And in particular, we are interested in a giant cluster, which, for example, in case of internet, there must be one at least, which contains most of the nodes in the network in one component only. And a giant cluster usually has two important properties. One is its size, which shows the performance of the network. So the larger the giant cluster is, the better the performance. And its existence at all, which shows if the network is performing its intended function, of course. So, for example, if the giant cluster doesn't exist on the internet, then obviously the internet doesn't serve its purpose, meaning that it should connect all the well, at least all the routers in the entire network. Okay, so there will be some mathematics here. Don't worry about it. It's just needed for the discussion. Some of them is going to be kind of trivial or at least known things. Some of them will be quite interesting and maybe even strange. Okay, anyway, so P sub k is the degree distribution. We know this definition from the early lectures, of course. Now, what we are going to have is U, which is the average probability that a node is not a member of the giant cluster through one of its neighbors. Okay, so U is going to be the non-membership probability. Okay, now U to the power of k is the probability that a vertex of degree k does not belong to the giant cluster, of course, because U was the probability that by one edge it doesn't belong to the giant cluster, and if it has k edge and with none of these k edge it belongs to the giant cluster, then this probability is U to the power of k. So the average probability of not being in the giant cluster can be calculated by this formula that we are summing from k starting from 0 up to infinity, pk times U to the power of k. So pk was the degree distribution, and U to the power of k was the probability that a vertex of degree k doesn't belong to the giant cluster. And what we are going to do is we are going to denote this formal sum with this G0U, which is, if you know this from probability theory, then this kind of function there is called a generator function. And this generator function usually has this form here. Now it's with Z instead of U, but okay, so this is just a variable here. So we are denoting here our variable probability variable with U. Okay. So, well, this was the probability of not belonging. So 1 minus G0 is the probability that a node is in the giant cluster. And so, of course, this could be claimed about the node which have not been removed yet, of course. Well, those which are already removed, of course, they cannot belong to the giant cluster, even if they were in the giant cluster. Right, so S, capital S, is going to be the proportion of such nodes which are part of the giant cluster. So S, how can we write it down? Well, this is going to be phi, which is the fraction of nodes which have not been removed yet. Okay, so that was phi, times 1 minus G0, G0U. So this 1 minus G0U, we just discussed that's the probability that a node is still in the giant cluster, and this is the fraction of nodes which are fulfilling this probability here. Alright, so we need to derive U, so we are interested in U. Okay, now how can we do that? we are going to denote a neighbor of a node by A. So these are going to be so for one particular node, A is going to be the set to which our node is connected. There are two possibilities, of course. The one is that A has been removed already. This has a probability 1 minus phi, of course. And A is also not part of the giant cluster. So don't forget that we are interested now to derive U, which expresses the probability of not belonging to the giant cluster. So A is also not part of the giant cluster, of course, because in this case none of its neighbors belong to the giant cluster, including our selected node. And if we suppose that A has again k neighbors, our neighbor, okay, of our selected node, then U to the power of k is the probability that none of them belong to the giant cluster. Well, again, this is the same argument which we used before. So the probability that our node is not part of the giant cluster through this node A. Sorry, like 2 minutes ago I was saying that A is a set of nodes, but no. This is just a neighbor of our selected node. So our node is not connected to the giant cluster through node A is 1 minus phi, which is this part, okay? So that A has not been removed yet. And the other part is phi times U to the power of k. So this is the other part. A is not part of the giant cluster. Right. So now there is something which we did not cover earlier in this lecture, which is called the excess degree distribution. Now we are going to call it QK, and this excess degree distribution is the probability distribution for a vertex reached by following an edge of the number of other edges attached to that vertex. Okay, so the formula for this QK is that k plus 1 times pk plus 1, which was the degree distribution, so the probability of a randomly selected node has degree k plus 1. Okay, so multiplied by k plus 1 divided by the average degree all over the network. So this was the first moment, as you might remember. Okay, so you could find this formula just coming out of blue, and indeed I have to say that indeed it's just dropped here without any discussion earlier. Sorry for that. If you are interested in the details, then please look up in the book of the course, and you are going to find the discussion about this excess degree distribution in details. So from here we can derive the following. So U is going to be, you need to believe in this, that a sum which consists of QK, okay, so this excess degree distribution, times, what was this part here, times S, which we, not S, the probability that our node is not part of the giant cluster. Okay, so that's going to be the formula which we are using, and so this sum is equal to the following. So if we take into the consideration that the sum of these QK values must be equal to 1, because this is a probability distribution, then the other, so I mean the expression itself equals to the following: 1 minus phi plus phi times k goes from 1 to infinity qk times u to the power of k. So you can see here that basically 1 and phi, they are independent from k. So what we need to take into account only the qk and the u to the power of k, so the multiplication here. And so as we know, so this is going to be 1 minus phi plus phi times, and now we are introducing another notation which is going to be g1u, which is the same as was before g0, but now instead of pk, now we have here qk. So all right, I hope it's clear that again, so like 1 here and phi here remains, because if we take the fact that this is going to be, so if I split this part into some qk times 1 and taking this equation here into account, then what I get is 1. Now if sum qk times phi, then again sum of qk is equal to 1, so what remains here is phi, and then the leftover is here. Okay, so this is now, of course it's kind of compact, but this g1 function here contains lots of details. Alright, so I was writing down here again the formula. Now it turns out that we can get the solution for this, in which please note then u appears in both sides of the equation. So let's take the first derivative of this function here, and we need to take the case where u is equal to 1. Okay, so let's take the derivative, and of course the derivative of u, I mean the derivative by u, is equal to 1, and this is going to be the derivative, so we don't know the formula for it, of course, but we can of course split this into 3 components. One is that the derivative of 1 is basically disappears, then the derivative of phi again disappears because they don't depend on u, and then what remains is the derivative of phi times g1u. And now, as I said, we need to take the formula at u equal to 1. And what is the reason why we need to take u equal 1? Well, so let's get back. So we are interested the average probability that a node is not member of the giant component. Okay. So so why we need to take u equal to 1 is actually explained in the book, and I just don't want to go into the details about that. So substituting u equal to 1 gives us this equation here, and from here what we get is phi is equal to 1 over g1 at g1 derivative at 1. So again, I was writing down this formula here, and then what we find that g1 derivative, what is it? So we know of course the formula for g1, and it's going to be the 1 over the average degree multiplied by the sum of k times k plus 1 times pk plus 1. And well, this is going to be the following. So again, 1 over the average degree times k goes from 0 to infinity, and k times k minus 1 pk. So what we were substituting here is the k plus 1 times pk plus 1 by this formula here. And without further explanation, just trust in this final result, then this is equal to the second moment of k minus the first moment of k divided by the first moment of k. By the way, there is a typo here, so this should be q k plus 1 and q k, and well, this is also a typo in the book, in fact. So anyway, the critical probability, so that's so the actual details about the derivation, well, they are of course interesting, but now we would like to just discuss the consequence of this derivation here. So if we substitute g1 prime at 1 here again to the formula, then what we are going to get is 1 over this formula here, so that's the taking the reciprocal of it. So we are going to get a critical probability, which is going to be the minimal probability that the giant component is there in the network. So this is the formula for it. And as you can see, what is there in the formula is basically all depends on the degree and such kind of things. So again, this is the formula. Let's see an example. In case of the internet, we need to keep this as low as possible, right? Because now the critical probability means that the giant components still exist, and then if we go above the critical probability, then the giant component will have some positive probability to be not existing. Now we know that the networks of internet routers are following Poisson degree distribution. So pk, the probability variable for the degree distribution, is equal to this formula. So that was the famous Poisson distributions formula. And here c is the average degree. So basically c is equal to this k first moment, and k second moment is equal to c times c plus 1. Okay, so if we substitute c and c times c plus 1 into this formula here, then what we get as a critical probability is 1 over c. Now if c is large, which is the average degree, then the network can really handle the removal of lots of vertices. You see, so for example, if we have only c equal to 4, which means that the average degree in the router's network is equal to 4, then we can remove not less than 3 over 4 of the nodes of the network, and then still we would get, with very high probability or good chance, we would still get a network which has one giant component, meaning that that a majority of the nodes are still remaining connected. So this kind of network is called robust for certain reason, right? Now, if we assume that the internet doesn't have Poisson degree distribution, then let's see the case that it follows power law degree distribution, and in particular, let's see the example where alpha is between 2 and 3 in the power law exponent. And we have seen this earlier lecture, one of the earlier lectures, that for power law degree distribution, the first moment is always a finite number, but the second moment, in case of alpha is between 2 and 3, then the second moment is always infinite. So let's see again the formula. So here, if we substitute infinite, or if you want a very, very large number, then basically the critical probability is going to be 0. So phi is equal to 0. So theoretically, this means that it doesn't really matter how many nodes we remove from the network, there will always be a giant cluster. Now, of course, this analysis is true for an infinite size network, basically. And nevertheless, it's very important that all the scale-free networks have this kind of property. So they are very, very robust networks, from robust for uniform random removal. Now, of course, in reality, where we have finite networks, then the second moment is always finite. Well, n is finite, so the number of nodes is finite. But anyway, even if it's finite, then still this is going to be very, very large number. And this means that phi is going to be a very small number, because we take the reciprocal of a very large number. Okay. Well, the opposite, the other example was the vaccination, where the robustness is not needed at all. So we would like to separate, of course, the nodes with the infected nodes. Now, unfortunately, in a social network we cannot control the degree distribution, so we can't tell the people with who to meet with and this kind of things, friendships. The only thing we can do is that we assume that it's power law. So we need to vaccinate that many people, which brings the network below the percolation threshold.